Hey everyone, so this is lesson number 8 in our Trig Identities unit. Today we're going to look at some more work with Trig identities, specifically how we can use our factoring techniques to help us with Trig identities. So before we can look at factoring with Trig identities, let's review our factoring. We have a couple different types that we've been looking at since grade 9. So we have common factoring. Common factoring is when we have some factor appear in every term in an expression, and we can take out that common factor. Here we have an x in both terms. We're basically dividing both these terms by x in order to pull it out, and then we write what we get left with. So we get a 7 plus a 5y. So we've taken out our common factor of x. Another big one that we've used over and over is difference of squares. Difference of squares, we have two terms being subtracted, or one term being subtracted from another. Both are squares of something. So 4x squared is the square of 2x. 9 is the square of 3. And we get our two sets of brackets, both at the square roots of those squares. And we get one bracket has a minus, one bracket has a plus. So 4x squared minus 9 would become 2x minus 3 times 2x plus 3. Trinomial factoring. This is more of the basic factoring that you would have had hammered into your head over and over again in grade 10. We have some trinomial, 2x squared minus 3x minus 5, and we want to basically unfoil it. We want to see what our two sets of brackets going to be. 2x squared, we know we need a 2x and an x. That's the only way we can multiply to get a 2x squared. Negative 5, we know we need a 5 and a 1. One needs to be positive, one needs negative, and we need to see what's going to give us a negative 3 as our middle term. So if I put a negative 5 here and a positive 1 here, we get a negative 5x. We get a positive 2x. Together that gives us a negative 3x. So that is our trinomial factoring. And then the final type, which again is really just like a special type of trinomial factoring, the perfect square trinomial. That is when we have a term like this, the only way x squared, the only way we can get that is if we have an x times an x, positive 1. We need to multiply either positive 1 or negative 1 and negative 1, and we know it needs to be negative because of our middle term, and that negative 1x, that gives us the negative 2x. So that middle term is the first part of the bracket times the second part of the bracket times 2. It's twice the first and the last in each of those terms. Because they're the exact same, we can rewrite it as a perfect square, x minus 1 squared. So those are the four main types of factoring. We did talk about some more complicated factoring this year with polynomials, but for now we're just going to focus on these ones and how this actually allows us to factor trig expressions. So if we have an expression like sine theta minus sine theta cos theta, we want to see, can we factor this at all? Well, we do have a common factor. We have a sine theta showing up in both terms, so we can basically divide both terms by a sine theta in order to pull out that factor. And then we would get left with a 1 and a minus cos theta after we pull out the common factor of sine theta. Similarly, if we have something like this, sine theta minus sine squared theta, again, we have a common factor of sine theta. We're dividing both the first and the second term by sine theta, which would leave us with 1 minus sine theta. One more example using the common factor. I have cos squared theta tan theta minus cos squared theta. I have a cos theta in both terms, so I can take out cos theta and I get left with cos theta tan theta minus 1. Those all use common factoring. We'll look at some using difference of squares. 1 minus sine squared theta. 1 is 1 squared. Sine squared theta is sine theta squared. So this would give us 1 minus sine theta, 1 plus sine theta. Similarly, if I have 1 minus cos squared theta, this would give us 1 minus cos theta, 1 plus cos theta. We're just using this exact same routine as we're used to, where we write the square root of our terms, and we have 1 minus 1 plus. And cos 2 theta, this doesn't look like a difference of squares right off the bat, but if we remember our cos double angle formula, one of the ways that we could write that was cos squared theta minus sine squared theta, which now that is a difference of squares. So that would become cos theta minus sine theta and cos theta plus sine theta. Our trinomials. Look at a couple examples using the trinomial factoring. So if I have 2 cos squared theta minus 3 cos theta minus 5, this might look a little foreign to us. Here, let's move it up a little bit. But this is really the exact same as this expression here, except instead of an x, we have a cos theta. Our first term is a cos theta squared, cos squared theta. This is just a single cos theta, and this one has no variable at all in it. So similar to how this is 2x minus 5 times x plus 1, this term would be 2 cos theta minus 5 and cos theta plus 1. If it helps, we can rewrite it and replace all the cos thetas with an x in order to see something that might be a little easier to factor. And that would give us that 2x minus 5 x plus 1. But eventually we want to get comfortable enough to be able to do it without subbing in those variables. So if you need to, you can write those in for now. We're going to get to the point where we don't need to use them ideally. Let's look at another one here. Cos squared theta minus 4 cos theta minus 21. Our first terms in both our brackets, we need to multiply to cos squared theta, so they need to be cos theta and cos theta. That's the only way we can get cos squared theta. Our final terms need to multiply to give us negative 21 and add to negative 4. So 21, 7 and 3, if we have a negative 7 and a positive 3, that negative 7 times 1 and the 3 times 1 together will give us negative 4, and negative 7 times 3 gives us negative 21. So this would work. And another example. 3 tan squared theta minus 7 tan theta plus 2. Again, there's only one possibility for our first terms. We need a 3 tan theta and a 1 tan theta, or just tan theta. And then we need to multiply to 2, and we need the sums to give us negative 7. So if we put a negative 2 here, a positive 1 here, we multiply, a negative 1. Negative 2 and negative 1. Negative 2 times 3 is negative 6. Negative 1 times 1 is negative 1. And then negative 6 plus negative 1 gives us that negative 7. So that would be our factored version there. And finally, looking at some perfect square trinomials. First example, tan squared x, minus 2 tan x plus 1. This looks awfully a lot like our example here. If we don't notice that though, the only way we can get this is a tan x and a tan x. The only way we can multiply to positive 1 is positive 1, or negative 1, negative 1. And we need negatives because our middle term's negative, and we get a negative tan x, which would together give us that negative 2 tan x. We get tan x minus 1 times tan x minus 1, which is the same as tan x minus 1 all squared. B, cos squared theta plus 2 cos theta plus 1 looks very similar, except we have that positive 2 in the middle. So this is going to be cos theta plus 1 times cos theta plus 1, because cos theta and cos theta together gives us that 2 cos theta. Cos theta times cos theta is cos squared theta. 1 times 1 is 1. And that's another perfect square. So cos theta plus 1 all squared would be our answer for B. And finally, C, sine squared theta minus 2 sine theta plus 1 looks an awful lot like our first example here. Eventually, I'm going to skip this step. We can tell it's already a perfect square trinomial. We have 1 of our variable squared minus 2 of our variable plus 1 would give us sine theta minus 1 all squared. Those are some examples actually using factoring, these ideas of factoring that we've come up with on trig functions. We're going to use these now on a couple identities and see how this can help us. Our first identity we're going to look at is sine squared of x over 1 minus cos x equals 1 plus cos x. Our left side, we have a fraction. There's a little more going on. We'll start off with that left side just because it's almost always easier to go from a more complicated version to a less complicated version. So sine squared x over 1 minus cos x. There's no sine x's popping up in our final answer. So let's use our Pythagorean identity and turn this into a 1 minus cos squared x. Sine squared x equals 1 minus cos squared x over 1 minus cos x. Well, now we have a difference of squares. 1 minus cos squared x, we can rewrite that as 1 minus cos x times 1 plus cos x all over 1 minus cos x. And now we have a 1 minus cos x being multiplied in the top, a 1 minus cos x in the bottom. We can cancel those out, and that will leave us with just 1 plus cos x, which was our right side. The left side equals the right side. We've solved what we're looking to solve. We've proven this identity. We'll look at another example here. 2 cos squared theta minus sine squared theta all over cos squared theta plus sine theta cos theta. Now, all of that equals 1 minus tan theta. Our left side is definitely more complicated. There's a lot more going on. So we're going to start off with that. And one thing that's good to note is we need to end up with two separate terms. Same as this one where we have two separate terms. This is telling us that this is all going to simplify down to two things being subtracted. There's a couple different ways we can go about it. One important thing to note is that our left side, again, we have a difference of squares happening in the numerator. So let's write that out and see what it looks like. So if we factor that top, we get cos theta minus sine theta times cos theta plus sine theta, and our denominator, we can pull out a common factor of cos theta, because there's a cos theta in both terms, and that would leave us with cos theta plus sine theta. That's good. We have a cos theta plus sine theta on the top, a cos theta plus sine theta in the bottom. That's going to simplify things quite a bit. We just have cos theta minus sine theta over cos theta left after the cancellations. And we know we need to get it to two terms. In order to write this as two terms, we can write both cos theta and the minus sine theta over our denominator separately as two separate fractions. Cos theta over cos theta is 1 sine theta over cos theta. That equals tan theta. So we get 1 minus tan theta, which is our right side. So we've proven this one. We're all good again. So factoring can help a lot of times make more complicated fractions a little simpler and allow us to start canceling things out. And that canceling things out is really an important strategy in taking something more complicated and making it simpler. That's how we're going to end up a lot of times going from a complicated thing towards a more simple term or expression. And it's a lot harder to predict what we need to multiply things by in order to go backwards. That's why we want to start off with the more complicated side a lot more. Look at a couple other examples here. On the next page, and I realize on the completed notes that this page is flipped, so I apologize for that. But perfect square trinomials can also be very useful. We've looked at a couple examples on this side in how we can use that perfect square trinomial and factor trig functions. There's one more example we'll look at of this factoring with perfect square trinomials. Cos squared theta minus 2 sine theta cos theta plus sine squared theta. Here we have sines and cosines happening. but we still have a trinomial, so we can still look at if we can factor this, same as our other trinomial factoring. So in both our terms, both our brackets, our first term needs to be a cos theta. The only way we can multiply two things together to get cos squared theta is we need cos theta and cos theta. And same for the last two terms. They both need to be a sine theta, or they both need to be a negative sine theta in order to multiply to a positive sine squared theta. And then lastly, our middle term's negative 2 sine theta cos theta. So that's telling us that these should both be negative. So if we multiply cos theta and negative sine theta, we get negative sine theta cos theta. If we multiply negative sine theta and cos theta, we get negative sine theta cos theta. So we have negative 2 of those sine theta cos thetas. And because it's a perfect square trinomial, we can rewrite this as that bracket squared. So cos theta minus sine theta all squared. So we'll look at this example here, which is secant 2x minus tan 2x equals cos x minus sine x over sine x plus cos x. We have two different sides here. We have this side using double angles. It can be fairly hard sometimes to get things to turn into double angles. So that, even though this side looks easier, that is a hint that maybe it's not necessarily as simple as it looks at first glance. But we also have this fraction with multiple terms in both the numerator and the denominator. So right off the bat, this is not a very easy trig identity. We have very different terms happening here. But I will talk more about the starting with the right side and going to the left, as it's a little less intuitive. So if you want to look at the other way, check that completed note. So we're going to start with the right side. Also, it's more consistent with what I've been telling you, where we kind of have more terms happening. We have a fraction. It's the side that immediately looks more complicated. So cos x minus sine x and sine x plus cos x. We can kind of cheat a little bit, and a lot of the times you're just going to need to basically experiment. You're trying to see what will work and what won't. Sometimes you'll have to try stuff and you'll realize that it's not going where you want to, so you might have to start again. And the more you do these, the more apparent some of these little tricks become. But one trick you can use is we can make a difference of squares kind of out of nowhere. So if I multiply the bottom by sine x minus, we want to multiply by cos x minus sine x, because that'll also give us a perfect square trinomial on the top. If we multiply by cos x minus the sine x, it's going to create a perfect square trinomial in the denominator, and we'll multiply the top by the same thing. And so our denominator, we're going to get cos squared x minus sine squared x because it's a difference of squares. And then numerator, because it's a perfect square trinomial, if we multiply that all out, we would get cos squared x plus 2 sine x cos x plus sine squared x. So we created a difference of squares in the denominator and a perfect square trinomial in the numerator. Now we still have quite a bit going on here. 2 sine x cos x. Oh, this should have been, sorry, this is a negative. Two sine x cos x, that is one of the double angle formulas. That is sine of 2x, and it's a negative, so it's going to be a negative sine 2x. Another identity that we've used a number of times, cos squared x plus sine squared x equals 1. So this whole numerator can be rewritten as 1 minus sine 2x. And our denominator, cos squared x minus sine squared x, that's one of the double angle formulas for cos. That is equal to cos of 2x. So this whole thing up here can be turned into these two double angle formulas. And that's good because our final answer only uses double angle formulas. So we know that at some point we need to convert everything to double angle formulas. We know it's two separate terms. We can use that trick from before and separate our fraction into two separate fractions, two terms that are both fractions. And that pretty quickly lets us see, well, the inverse of cos 2x is secant of 2x. Sine over cos of something is tan. So sine 2x over cos 2x is going to be tan 2x. And that gives us our left side. And so we've proven what we needed to do. It only took a couple steps. Some of those steps are some pretty big leaps. So take your time and go through that and make sure it makes sense to you and let me know if you have any questions. But we've used quite a few different tricks here that might be new at this point. So take your time and look through that and make sure that sounds okay. I'm gonna look at one more here. Tan x plus secant x squared equals 1 plus sine x over 1 minus sine x. Again, we have two pieces that are a little more complicated. They're really quite close in terms of how complicated they are. I tend to like to start with fractions and work away from them because generally I find it easier than working with fractions, but it's really up to you. So again, in the lesson, there's something that starts with the left side. I'm going to start with the right side. I'm going to start with this 1 plus sine x over 1 minus sine x. And so again, we're going to use this trick to come up with a difference of squares in the bottom. So we're going to multiply by, they call it the conjugate. So you're basically multiplying by the same thing, but with a different sign in order to create that difference of squares. So I'll multiply both the top and bottom by 1 plus sine x. And so in the denominator, we're going to get a 1 minus sine squared x because it was a difference of squares. And in the numerator, we have a perfect square, 1 plus sine x squared. 1 minus sine squared x. We know we need everything to be squared in the end. So that's a hint that the top's already squared. We need the bottom to be squared as well. So 1 minus sine squared x, that's the same as cos squared x, or cos x all squared. And so by changing it to that, our top is something squared, our bottom's something squared. So it's the same as this whole fraction, 1 plus sine x over cos x, all being squared. That allows us to have everything be squared. Now we just need to see how we can get this inside, the 1 plus sine x cos x, over cos x to equal tan x plus secant x. Again, we have two separate terms. So that's telling us we should separate into two separate fractions. And we'll see if this gives us what we want. 1 over cos x is secant x. Sine over cos is tan x. And it's written in a different order, but this is equal to our left side. Tan x plus secant x all squared. So we've solved this one as well. This is a look into some more complicated trig identities and how we can use math that we've learned over the years in high school to really be able to prove even more complicated stuff that you wouldn't have been able to prove last year. Again, let me know if you have any questions. Hope all is well at home and that you're getting to enjoy some of this nice weather that we've been having over the last week or so. You'll hear from me in the next video. Goodbye.